Is this like the problem of the day? Or?
This is what we just want to talk about. This is from the homework last time. This was number 40. And you were supposed to prove this property, right? And I want to talk about, there are two different ways you could go about doing this. One is with components, right? Where we rewrite A and B as A1, B1, and, you know, or A1, A2, B1, B2, right? Where we have this type of thing. A1, A2, plus B1, comma, B2, and then we have dot, and I'm not going to bother to write the next one out because I want to go ahead and just do this step. What is this? If I were to add these together,
A1, B1.
A1
Plus B1.
Plus B1, and then
A2 plus B2.
A2 plus B2, and then that would be dot what? I'm not going to bother with that step. Let's just jump to the chase.
A1 plus B1. A1 minus B1.
A1 minus B1. There we go. A2 minus B2. And so this is one way we could go about doing this, is just component-wise, right? And actually, and you might think, yeah, that might work in 2 dimensions, but if you get above 3 or 4, this is going to be a real pain. But what you could do, though, is really, in that case, if you did have really big vectors, you would just do like this type of thing. And then as you're doing this, like instead of writing A1 plus B1, you would probably just write it as A1 plus B1 dot 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 all the way down to AN plus BN. And you could still do it component-wise, understanding that you're following the same pattern for all the other ones. And you could do it. It's just eventually, component-wise, kind of can get a little unruly, right? And though it's perfectly good to do, and that's, you know, this is the way we're gonna go about doing this one. Make sure we're recording. Okay, I did press record. So, okay, definition of dot product. What is that? I have 2 vectors dot each other. What is this?
First one is a difference of squares. The
Well,
first
hold
one
on.
times the second one plus the second. And the first one, well, the first one.
The first component, whatever this component is, this times this, right? And so I'm going to go, okay, A1 plus B1 times A1 minus B1. And then plus, then I do the same with the next component. And if there was more to it, if this were a 3 vector, a vector in 3 space, there would be another component, and I would just do the same thing, and so on and so forth. But in this case, it's A2 plus B2, A2 minus B2. Now we're in the realm of real numbers. We are out of vectors now. This is just some real, these are all just real numbers. And so our old familiar rules apply. And I could just say, okay, I could first outer, inner, last. I do first, I get A1 times A1 is A1 squared. And I'm going to go ahead and jump to the chase. We know that A1 minus B1, A1 times minus B1 plus A1 plus B1, they cancel, right?
It's minus B1 squared.
Minus B1 squared. Same thing happens over here. I have a plus, and then I go A2 squared, outer, inner, cancel, and I get a minus B2 squared. And so rearranging, now it's like, okay, now what am I doing? Well, you know you're trying to prove that this thing is equal to that thing. So I'm thinking maybe I group my A's together, group my B's together. So that's going to be my next step. A1 squared plus A2 squared minus B1 squared minus B2 squared. Is that the same thing as that?
Yeah.
Because A dot A,
Oh, A dot A is.
A dot A is, let's see, A1 times A1, A1 squared, plus A2 times A2, or A2 squared. So yeah, that is the same, that right there is the same thing as A dot A. Now I'm going to take another step and go minus, these are just real numbers, B1 squared plus B2 squared. And now it's easier to see that that's the same thing. By the same reasoning, that's the same thing as B dot B. And so we have A dot A minus B dot B, which is exactly what we wanted to show. So that's one way you could do it, just component-wise, just straight up brute force, just use the definitions of stuff. with the components. But another thing you could do, and usually, and as you go on in math, this is the type of thing you'll do. You'll remember for this last homework, I had you prove the box on page, I think it was 606, right? That had all these new properties of the dot product. And what you'll do, you'll find, like, as you go on in math, you'll get like a bunch of new properties of some new object that you're working on. Like in this case, we're doing vectors. And you'll have a bunch of properties of vectors and stuff. And then as you go on to do work, it'll be like, you know, prove this new property that wasn't one of these. And what you'll often find is that it'll make your life a lot easier if you use these properties that you've already proved to prove the new thing. So that's what we want to do. That's what I'm going to do here. Another way of dealing with this is to use the properties that we've done before, or that we've just proved about the dot product. Problem is, well, there's a couple problems. Is that we've proved something like this, that u dot v plus w is equal to what?
uv plus uw.
U dot v
Oh yeah.
plus u dot w. And the thing is, like, that the thing that we proved is that that's a plus. And another thing to note, like this right here, any two vectors, you add them together, you get another vector, right? So this right here, we could just rewrite that as u dot something. And so, but the only thing we have here is, so the thing is, like, what happens with the subtraction? Is it what you think it is? If I replace that with a minus, do we get a minus there? Does that work that way? And so, one thing I would like to just verify beforehand is that that is the case. What if it were, what is u dot, let's say, v minus w? I look in the book, there's nothing about that. We only have this one. But I know that minus w is the same thing as plus negative 1 times w, right? And so I could rewrite this as plus negative 1 times w, or some constant times w. And then our rule just tells us, well, that's u dot v plus u dot negative 1 times w. But you've also proved that this times, right, in one of the properties that's there is that u dot mv is the same thing as m times u dot v, right?
Yeah.
So there's no difference there. You could say, oh, that's the same thing as u dot v plus negative 1 times u dot w. But negative plus a negative does work like real numbers. That's basically how we define subtraction of vectors. So we get u dot v minus u dot w. Thing is, we don't know that about vectors until we actually go to prove it. And notice in this case, I didn't bother with any components or anything like that. My life is a little bit easier because of that. But it's only because we've built this up already. We've built up all these properties, like and in your case, you proved each one of them for your homework. Now that we've done that, let's use that to our benefit. And that's what, now I've verified that yes, if you have u dot v minus w, so any vector dot a vector minus another vector, then that's the same thing as basically it distributes over subtraction. The dot product distributes over subtraction. That's what we just showed here. Now that I know that's true, I could say, well, this thing itself is just a vector. I could rewrite u here if I wanted to and then go substitute it in later, but I don't want to do that. I'm going to say, okay, well, that's just some vector and it distributes in, right? So this is the same thing.
You can just FOIL.
Well, no, that's what we're trying to prove. We're trying to see if we can. Like, well, yes, that's what we will find out, but first we have to distribute it over because that's the only thing we've proved yet. We don't know whether or not we could FOIL it. It turns out to be true with the dot product. Not true with other types of products, but in this case, it does work, and we'll see that. Well, we'll kind of see it. But now, okay, now we have the same, we have this vector dot this vector, this vector dot this vector. And yes, actually, and you might say, well, hold up, we proved A dot B plus C, it distributes this way. Do we know if it distributes this way? It turns out it does, because we've also proved that any two vectors, u dot v, is the same thing as v dot u, right? Like, and so these are things like, it turns out with vectors and the dot product and stuff like that, this is very much like the stuff you've seen before. Very few times does anything come up where, oh, you can't just do that. It absolutely does happen with matrices. Like, you can't just assume that, oh yeah, I could just distribute it over. Well, does it distribute that way? And if it distributes one way, does it distribute the other way? And so I'm not going to go through it, but we could just say, this is the same thing as that, and so then it comes in, and you could see that it would be the same thing, right? But yes, it does distribute back in this way, and so we get A dot A plus B dot A minus, now I'm minusing something, so I'm going to go ahead and put in brackets everything that's I'm going to do here. That would be A dot B plus B dot B. Now I'm subtracting this, and there's another thing, right? These are no longer vectors, right? Because A dot A is a real number. B dot A is a real number. Any vector dot any other vector is a real number. And so that's a real number, that's a real number,
So it's just real numbers.
that's a real number. And now from here on out, now we're just talking about real numbers. And so everything we know about real numbers applies. This is just minus a real number plus a real number. And so this is the same thing as A dot A plus B dot A minus A dot B, and that distributes over to give me a minus B dot B. Now can we cancel those?
Yeah.
We can, and that's only because we've already proved that A dot B is equal to B dot A. So if you wanted to be really clear here, we could say, well, B dot A is the same thing as A dot B. And so I'm going to say, I'm going to take this step, not really necessary, but I'm going to do it just to be sure. Because when you're starting to work with new objects, new mathematical objects, you cannot guarantee that it just does what you think it's going to do. Right? Like when I look at this, I think, oh, you're taking something that's a sum, multiplying it by something that's a difference. I know what to do. You first outer, inner, last, the inner, outer cancel, and you should end up with this. Maybe, maybe, I don't know. These are vectors. They don't work like real numbers. But what we're starting to see now is, yes, they will, because here we go. This is the same thing as that, plus that real number minus that same very real number. They do cancel. And now I'm left with the thing I wanted to prove. That A dot B minus B dot B. So there's two different ways you could do it. The thing is, you cannot just say, oh, I'll just first, outer, inner, last. Like now we know that you can, but we didn't know that ahead of time, right? And so, like if we had done this with a C plus D, we'd have to go through all the same stuff, and you'd see that it's the same thing as first, outer, inner, last, but you have to take these steps. Cool? Everybody good on that?
Yeah.
Okay. All right. So you guys got the homework copied down?
Yes.
Good, good, good. All right. So I wanted to start off with this, and I think I'm going to change this up just a little bit. Here's something. Here's another thing. And this angle is theta. Now, let's say that this length right here is, I don't know, let's just call it A. That length is A. And what I want to find is this length right here. And I'm not trying to be tricky. This is what you think. It is, if I were to drop this right down there at the same length, it would be a right angle. In terms of theta and A, what is that? What is that length?
It's sine of, and cosine of,
Let's just start with cosine of something is equal to what?
cosine theta equals that length.
The length that I'm looking for, let's give it a name. Let's just right now, we'll call it L for length.
L
Length.
over A.
Over A. And so the length itself is equal to
A cos.
A times cosine theta. That's the length that we're looking for. Okay? Okay. Now, let's change this slightly. Let's say that this is a vector. And we'll name that vector A. And let's change this and call this a vector B. It doesn't matter. I don't think we use this length at all, but I'm just going to do that anyway. Now, how does this change?
Well, A is no longer a real number.
A is, well, first off, A doesn't show up anywhere on
You
here.
need the magnet.
And so what do I do? How do I, it's the magnitude of A, right, is what that length is. And so that changes this to be, well, it's the magnitude of A, right there. And this would be the magnitude of A, is that length right there. Okay? Okay. So we're all agreed that that length is equal to the magnitude of A times cosine theta. Actually, it has nothing to do with B, right? B could have been another mile longer that way. It could have been really, really short. I mean, that length would be the same. It could actually be pointing in the opposite direction. This length would still be the same. Okay, that's all I said. I just want to know in the direction. So you kind of think about it as like if I took a light and shined it down on this vector, like how long would the shadow be that this vector casts onto this vector? This has a special name, a special symbol, and it's a real pain. Did I want to actually write? I did. Okay, so I'm going to do definition. Definition. If theta is the angle between two non-zero vectors, that's important, non-zero vectors, say A and B. Okay, so that's set up right there. You have two vectors, they're non-zero, there's some angle between them. Then we define the component of A along B. And we have a nice fancy way of writing it. It's comma. Now watch how I do this. This is how I like to do it. The component of A, kind of like how you do of, like this. Again, some function of what? Of x of A, and then look, this is the pane along B. Little subscript B. Right? This is standard. This is what it was. But the component of A along B is defined as that length right there. And it's equal to this right here. Ta-da! Okay? Now this may seem like a really arbitrary thing to define, and why would we care? You'll see. Okay, it's actually, yeah. And so now look at this. This right here is a real number. You can also think about it as given any b, it's a function. You plug in, given a b, some vector somewhere. Now you give it any other vector a, and you have something that's well defined. You could say, well, there's some length given any vector a, and that length is this. But the thing to note is that this is a scalar, right? It's just it's a length. There's no direction involved here. If I take the magnitude of something, that's just some number, let's say 2, and then I say, let's say cosine theta, and maybe theta is like pi over 3, then this would be 2 times a half. It would just be 1. There's no direction involved, although you happen to know that it is in the direction of b. But the thing is that this thing itself, when you see that, the same way as when you see something like this, a dot b, you know that that thing right there is a scalar. That thing right there is also a scalar. So that's important to keep in mind. But, so now, that's what I'm going to do. I'm going to say this is the same thing as the component of A along B. Okay? Everybody got that? Okay. What would, so kind of graphically here, and I'm going to this. I made that a bit too, let's say that's B. What would, graphically, what would the component of B along A be?
Would be. Wait.
Well, it's, if you just, all we did is we just projected A down onto B. If we did the same thing here,
Oh.
right, we could project this guy so that there's a right angle, so that we make a right angle in this right here, that length that makes a right angle, and I'm trying to do this while looking at it sideways, so it might not be perfect. But that right there, that would be the component of B along A. That's all you're doing. You're just projecting the length of a vector into the direction of another vector. Okay? And here, you tell me, what would the formula for this be?
Magnitude of B.
Yeah.
Cosine.
Yeah.
Theta.
Yeah, it's still cosine theta. Right? And you can see that if you did this, and you go, oh wait, okay, yeah. Adjacent over the magnitude of B, right? Cosine theta would be adjacent over the magnitude of B. And so that would be the adjacent side. And we do the same kind of thing in order to find it. And yeah, that's all that is. So we're going to play with this a little bit longer. Now, here's another thing to notice. If B were longer, if it were something like this, if this were A and this were B, then yeah, it would, the projection of B, well, it's not the projection, it's the component of B along A, would actually be longer than A. That's perfectly fine. That could happen. It's just, that's the, we call it the component. Okay? Another thing you could do is, well, what if they're kind of, what if you have an obtuse angle between them? Something like this. There's theta. If this is A, and if this is B. Well, now, we're not projecting it, like if I want to project A, sorry, if I want to find the component of B along A, if I shine a light that way, it doesn't really work. I have to shine it back onto the direction of A. Because remember, or one way of thinking about this is that this is a direction. It defines a line that goes through all of space. And then in order to find a right angle there, then this would be the component of which along which?
B along A.
B is being projected onto A, so it's the component of B along A. And then doing it the other way, since this is the direction of B, then projecting this guy here, that a little bit is the component of what on what?
A along
A along B, right there. Okay. So that's, so now here's the thing, like I made a big fuss about all this geometry stuff. It's not really, like, yes, there will be times where it'll be very helpful to think about it this way, but in general, like, the nice thing about this is, like, we've done the work, now we have a formula. And this is usually how you're going to see this stuff, like, to just, I hate to say just plug it into the formula, but you could really you could really break your brain if you think about the geometry too much here. It's one of the few times I'm going to say you could kind of leave this alone as long as you get the general idea that this is what this does. So just be careful. Okay, so now check this out. This is the cool thing. This is where it gets interesting. same problem. We want to find this length. But let's say we don't know what theta is. Let's say we also know what the magnitude of b is. We know the magnitude of a. We know the magnitude of b. And I want to find this length right here. In other words, I'm trying to find the component of a along b, but I don't have theta.
You can find theta with tangent. Or no, with not tangent. Cosine. Cosine of theta equals magnitude of b.
What is theta? Where's theta? Oh, I see. I see what you're saying. So, what now?
The
Cosine of
cosine of
theta?
theta equals the magnitude of b over the magnitude of a.
No.
Or
No, not even close. Because what if the magnitude of b were 700 and the magnitude of a were 1? Then you're telling me that cosine theta equals 700 over 1 so that you plug something into cosine and it'll pop to 700? No.
oh,
And there's no right angles here either. I mean, there may be. It might be a right angle between it, but just this idea of cosines and stuff like that, like, we don't have any of this right now. We don't know what theta is. There's no way of finding theta. I mean, maybe there is. Sure, there probably is. But there's a much easier way of doing this. And this is what I'm getting at. This was kind of cool about this. Is remember, from last time, A dot B is equal to what?
a wait. Oh. Wait.
Magnitude of
Magnitude of A, magnitude B times cos theta.
uh-huh. And now this is the thing we're trying to find. So if I divide both sides by b, I'll have A dot B divided by the magnitude of b is equal to A cosine theta, but that's the value I'm trying to find, right?
Yeah.
That is that length that I'm looking for, that length that we're calling the component of A along B. So here's a way you could get the same exact thing without knowing what theta is. In fact, I'm going to come back and say, or, so back to our definition, you could just say the component of A along B is A dot B divided by the magnitude of B, right there. So one of these is useful if you happen to have the angle. One of them is useful if you don't, right? Right. Okay, so we got that. So we already said that the component of B along A was equal to B cosine theta. But just looking at this formula, how can I change this up to give me the component of B along A? It's what?
B A times B over the magnitude of A.
A what B?
Dot B.
A dot B over
The magnitude of A.
magnitude of A. There you go. Right. There we go. So there's the geometric interpretation. It's just a length. If you project one vector onto another vector, the length of the shadow that you would project onto. If you're projecting perpendicular to that other vector, what length of shadow would that make? That length is what we call the component of one vector along the other vector. Okay, so let's do an example. Let u equal 1 comma 2 and let v equal -2, 3 and let w equal 1 comma 1. And we want to find component of u plus v along W. Do we have any thetas? No, we don't. No, we don't. So, probably want to use this one. Right? Otherwise, or you could go find data. And then, you know, you will have done a lot of work. This is so simple. Like, if you ever have the chance to use this one, just use this one. As you'll see, it's really easy. But the problem is, we don't have anything for a plus something.
Or you can just add them.
There you go. Thank you. Thank you. This is, I'm alluding to I'm trying to shore up some, there's a homework question which could really mess you up if you're like, wait a minute, is that the same thing as the component of one of them plus the component of the other one? And no, it's not at all. It's not even close. So you could really break your brain if you think too hard about this. What is u plus v? Just tell me what in component wise.
Negative 1, 5.
Negative 1, comma 5. There you go. So now we have the component of some vector along another vector. And let's just use that bad boy right there. So it'll be, I'm just going to do it as the dot product of this one, negative 1, comma 5, dot W is that one, 1, 1, over the magnitude of, it is the one that's in the bottom. This is how I keep it straight in my head, I think. It's the magnitude of which one? Which one's on the bottom? Right, of these two, we're in that direction, that's the one that goes on the bottom. So it's that one right there, 1, 1. Okay, so let's actually do that dot product. What do we get? First one is negative 1 times 1 is negative 1. And then
Plus
5. What's the magnitude of 1, 1?
1.
Square root of 2.
Square root
Yeah,
of 2. Yeah, okay. So that's what, 4 over root 2?
Yeah.
Which, okay, we could be done there. Or you could say that's the same thing as 2 root 2. Right? Because you have 2 times 2 over root 2, which is the same thing as root 2 times root 2 times 2 over root 2. One of them's gone, 2 root 2. Okay, so there we go. I'm going to go ahead and put that up there. Now, let's look at this graphically. Like, in your homework, that's all there is to it. Okay, there's a few questions that are just like this. Just find that, and you just do it. That's all there is to it. But I do want to look at this, though. What have we done? Okay, we're finding the component of u plus v, which is minus 1, 5. So let's do it like this. There's minus 1, and we'll say 5 is there. So we're finding the component of that along 1, 1, which is like here. Right, there's 1 and about 1. Now this is not perfect. And what did we find? Is that it's 2. What is, and you told me that the length of that is what? Root 2. Root 2. And so yeah, it sure does look like if I projected this guy down onto here, then the resulting length that I would have should be 2 times that amount. Of course, I did not draw this very well. I just eyeballed it. But if you were to draw it very well, use graph paper, you'll see like, yeah, that's what's happening here. So again, your homework is not really going to be concerned with the geometric interpretation of all of this. But it's just good to know this is what you're doing, and you're finding this, and it all kind of works together. Questions? If you ask me, this seems like a completely arbitrary thing. Like, who cares? Where did this come from, and why do we care? Why are we learning about it? Like, I don't know. I'm gonna keep going. I'll keep going. Okay. Here's why. There's another definition. Now, we're going to get, this is what I'm going to call the scalar version of what we're about to define. We're going to get a vector version in a minute. This is the scalar version. If a constant force, call it F. Notice that's not a vector. That's not, I've not put a little arrow over it, so it's a scalar. If a constant force, F, is applied, to an object, okay, so like what's happening? A constant force applied to an object. So I'm applying a constant force to this object right here, okay? Moving it a distance d. So this is what's happening. I'm applying a constant force to an object and I've just moved it a distance d. In the direction of the force. Notice I pushed exactly this way and it moved exactly that way. I wasn't pushing this way, then this definition doesn't work. It does not work. If I'm pushing this way, my direction of force would be going in this direction. That's not what I did. I pushed in the exact direction of motion. Okay, so that's the setup for what this is. If this is happening, this right here, if that's happening, then, and this is in the direction of the force. I'm going to underline that because that is key here. Like I said, it's different if the force is being applied in a different direction from the direction of motion. But if it's being applied in the direction, if it's moving in the direction of the force, then what? The work is given by F times D. You just multiply them together. And I'll be careful. I don't want to use a dot because I don't like we're talking about the dot product, but you just take whatever that force is times the distance, and that's what we define to be the work. So force times distance. And these are not vectors.
What's the work?
That's the work. We're going to talk about this in just a second. Here, buddy. Hey. Thank you. And what is force? So, here we go. Work, sorry. So we have force and distance and work. There are different units you could use, and depending on the units, you have different things. So, for instance, if your force is in pounds, and your distance is in feet. So you imagine, I have this book, and it's roughly, feels like 3 pounds maybe, 3 pounds, okay? I have 3 pounds, and now if I lift it up 1 foot, right, I've done work. How much work? Well, 3 pounds times 1 foot would be 3 times 1. What do we call these? They're called foot pounds. Foot pounds. That's just what it's called, right? It's ridiculous. Foot pounds. Now, there's another measure of force, a dyne, whatever. And with dynes, you use centimeters. So this has, I'd have to use some force, however many dynes it is, to move it up however many centimeters. And then that work would be an erg. Erg. Nice.
Not dyne centimeters.
Nah, that's what it is. It's dynes. It's and its units are dyne centimeters.
How many dynes in a pound?
I have no idea. No idea. Now here's the one that here's the one. This is standard. So the SI units. Have you heard of SI units, standard international units, which are, things like meters, kilograms, stuff like that. Volume would be liters, and so on and so forth. The standard unit of force in the SI regime or whatever is called a Newton. Big capital N for Newton.
Oh,
Newton. Length, standard, is meters. And the work is Newton meters. Newton meters. But this has a special name. It's called a joule. It's a joule. A joule is a Newton meter. So if I apply however many newtons to push this thing and I move it, say, 1 meter, then I've done however many joules of work. Okay? A Newton, I believe, is a kilogram per meter squared? No, a kilogram meter per second squared. Kilogram meter per second squared. Because it's acceleration. It's how fast can you accelerate it. So, take a kilogram, which is about 2.3 pounds, and move it 1 meter, and so that it moves in 1 second. You move it 1 meter in 1 second, you've done 1 kilogram, 2.3 pounds. You move it 1 meter over the course of 1 second, so 1001. That is 1 Newton of work right there. Or you've done, well, no, that's work. It's like that, or that's, I think, yeah. Kilogram per second squared is a Newton. And then kilogram meters per second squared is a joule. Something like that. That's a way to think about it. I'm sorry, I should have looked this up right before we did this, or as I was writing the notes, but I didn't. Whatever, that's a joule, okay? But it's this idea, right, that if you have a constant force, and now notice it's not like I push real hard, then I slow down, and then I push, like that's different. That's completely different. But if I'm applying a constant force to something, and it moves a distance d, then that force times the distance is what we're calling work. And it is energy. It is energy. Joules. Like, that's the same thing as, like, that's what, well, actually, joules over a certain amount of time is what the power company measures when they check your meters and charge you money. Okay. Now, here's one thing I want to say. This right here, work equals force times distance, only works, like I said, when it's in the direction of the force. So imagine I have a car, and it broke. And so I have a rope that I'm going to attach to the car, and I'm going to pull the car. Okay, and holding on to it. Okay, now, if that's, I guess it's a collar, I don't know, but like, here's the thing, right? So, let's say I'm pulling with a force of 50 newtons in that exact direction. And that exact direction happens to be the direction of motion. And let's say that I pull that car a total of 100 meters. How much work have I just done?
50 times.
There you go.
50.
50 newtons
5,000.
times 100 meters would be 5,000 Newton meters, which is 5,000 joules of work. Okay? Your book is not concerned about units with any of this. It's just going to say 5,000. Okay? But here's the problem. It's like, in order to do that, I would really have to hunch down. And I'm probably not going to hold it like that as I move along. As you can see, I've drawn it that way. It looks better right here. It looks like I'm really crouching. But in the real world, things don't always work that way. In the real world, I might be a little bit taller, whatever. Or I'm not, but somebody might be taller. Noah would be taller. and would look more like this. If Noah's doing this, he would be. I guess you're biting it. It looks like you're like this, right? So here's the thing: the force that you're actually pulling on the rope is in that direction. It's kind of like in the same way, like when I pushed. If I were to push on this that way, I'm pushing down also. The force isn't purely in the direction of motion. Some of the force is going down this way. Some of the force is going this way. And so now we have a different scenario because the force is in this direction, and we'll say it's like 50 newtons. But now, well, it's not going in the direction, so what are we going to do? So it turns out that the work is the component of the force in that direction. So if you think about it, if you take this vector, right, this vector, and you break it into its components, it's going to have an upward component, right? Kind of like the same thing, if I'm pushing on it this way, some component of that is going straight down. Another component of it is going this way, but it's kind of like you've added those two components together to get this, right? And so if you split that back up, you have an upward component of it, and you have a purely, in this case, horizontal component. Or that the component, and this is we're gonna call this the component of, and let's give this, that's my force vector, and let's call this my distance vector. This would be the component of the force along the distance d. And so now that we've taken that vector and split it into its different, you could split it into the other component, but we're going to do it into this direction. Now, whatever length that is, that's the magnitude that you're looking for. That's the magnitude of the force that is in that direction. And so what we could do is say, well, if you find that component, we could pretend that you're not actually pulling in that direction, that you're actually pulling in this direction, and then this applies. See? You get that? You guys get that?
Yeah.
Right? And so it's like, yes, in the real world, you're actually pulling up, or in the real world, I'm actually pushing down on this thing. But we could pretend that we split this into its two components. We could split it into this component, and we could split it into this component, and then we say, well, it's as though you just had this component, and you've moved it this far. And so now we're back there, and we could just say, take the component of the force that's in the direction of d, and multiply it by that. So, what did I just say? Well, this now let's do this a little bit more abstract, and remember that I can move vectors around. Right? So forget that my bumper's right here for right now. And what I'm going to do is say, hold up now. Why don't we take this vector to be as long as the actual distance? So then d now, the length of d is 100. And my force vector, we know it has a length of 50, or whatever. The magnitude of the force is 50. Right. Then what we do is we find, like I said, the component of this along that. We say the component of F of the force along D. And then we just take that and multiply it by the length of D. Yeah? That's what this would be, right? So in other words, this is kind of like your lowercase d distance from earlier. And this thing is like your, it's like the magnitude of F, but it's in the direction that you care about. Does that make sense, what I'm saying? Right? So in other words, the force from up here is then this bit right there. It's the component of force that's in the direction of D. It's right. That's what that is. I made a big fuss about this to really show you, like, this is the same thing here. Like that, this force in the direction of that. That's just the component. That's how we define this. That's the component of the force in that direction. So watch what happens. What happens to work when I do that? We have F, which is the component of the force vector along D, times the magnitude of D. But let's use that and see what that is. Check this out. The component of F along D is whatever F dot D is over the magnitude of D times the magnitude of D. Yeah, did I do that right?
Yeah.
F is the one that shows up there.
Go away.
D is the one that goes there. Oh, and look at that. And so, the work is simply the dot product of those two vectors. Isn't that cool? That's really cool. So, we could say then, definition in the vector version. So, here, just show it. We'll do it right here. Vector version. The work. Done by a constant force. Still has to be constant force. You can't be pushing and then going. It has to be a constant force that you're doing. The work done by a constant force A, and that's a vector force. At its, this is a little weird, and we'll talk about this. At its point of application. Oh, no, I'm sorry. As its point of application moves along vector V. I'm sorry, moves along vector B is the work is A dot B. So clearly, if you're applying force to something and it's moving through a distance, it's moving along some trajectory. Okay, so like this one, I'm pushing here and it's moving in that direction. This would be its point of application. This is where I'm applying the force. And as it's moving along its, so if we imagine, here's my finger, the force from my finger, and it means we have 9 minutes. So right there, as it moves along this direction, that's the direction vector, right? Like, as you can see, that's, like, I'm trying to draw this. There's my force right there, and there's its direction. It's moving like that, right? Then, remember, we can move vectors around. This is just F dot D right there, okay? Or A dot B, whatever. So you have a direction vector, and you have a force vector. So here's an example similar to number 30. Okay, I'm going to get rid of all this. So it's just force times distance if it's done in the direction of the thing. But if you have vectors, it's dot. That's very convenient. It's very, very convenient that it just works out that way. So this is similar to number 30. This is approximately like number 30. C, oh, this is such a pain. C represents constant force. Now, find the work done if the point of application, oh my goodness, point of application, okay, it's all written there in those like 3 that you're doing from this. Find the work done if the point of application of C moves on a line segment from P to Q. So this is the setup for these types, okay? So you're imagining you're doing you're pushing some constant force, and then the point of application moves from point P to point C, okay? So there's my force vector in this direction. This right here was point P, and its end point was point Q, okay? And then it gives you something like this, C equal to negative 10 I hat plus 12 j hat. And from now on in this class, anytime it says to do something with I hat and j hat, you could just use the regular old angled brackets. I am fine with that. I want you to play, get kind of used to it, and then we're going to forget about it. So as far as I'm concerned, that's negative 10 comma 12. Okay, so let's think about what's going on here. You have something here at 4 comma minus 2, so that's point P. Q is 8, 5, right there, there's the point Q. And we have some force that's in this direction, minus 10, 12. Okay, so minus 10, 12, something like that. And this is, of course, I'm not drawing this to scale, but there's the vector C. And so we can imagine that you're applying some force as this thing is moving along this straight line right there. And you can imagine, like, well, it doesn't look like it's doing, like, why would it move that way? Well, the same way that I kind of do this, and it would still move, right, even if I'm pressing in a weird direction. Or maybe there's other forces that are moving on it. Maybe this is actually a ship that's moving, like a big tanker ship that's moving along here, and there's a little tugboat pushing on it, Maybe that's what's going on. There's a billion different things. But its point of application is moving from here to here. So then the thing we want to do then is say, we have our force vector. Like what we want to find, we have a force vector. Now what we need is a distance vector. And if we could get a distance vector, then C dot D would be the thing. How do we get this guy right here? Oh, and notice, notice what I've done. I look where I put its tail. Normally, if I did this, I would go from here 10 up 12. But what did I say we could do with vectors? I mean, you can move them anywhere, right? And so, another way of thinking about this, we could have started with C like this. And then we just find out this displacement, and then we could move him to the origin. What would that displacement be? Think about it. Like if this were on, if we redrew the origin to be right here.
8, 5. This would be root 64 plus 25.
I don't care.
Wait, no.
I want to know what direction that is. And one way we could do it is we just find the displacement. Take 8 minus 4, right? Right? 8 minus 4. So you go Q minus P. And so then this new vector that I'm trying to find, which would be my distance vector, would just be this one minus that one, which is 8 minus 4 is 4. And then 5 minus negative 2 is 8. 5 minus negative 2 is 7. And now, there you go. Yeah. Take the dot product of those two bad boys, and you get 44. Right? Okay. Right, because that one's negative 10, 12. There you go. Okay? So that's the kind of thing you're doing, okay? And like you see like how this all kind of works. This is kind of why it's nice that you could just slide vectors around. Because this vector, it might be from here to here, but you could say, well, we could just pretend it's here. We could pretend it's at the origin. In that case, what is this length there? Well, it's the distance from P to Q here. From P to Q is a distance of 4. From here to here, it's what? Well, it's from there to there, right? 5 all the way down to minus 2 is 7. So you have 7 high You have 4y. That's the same thing as going 4 this way, 7 this way. Does that make sense?
Yeah.
Okay, here's an example like 31. So this example is very much like 41. This is similar to number 41. Okay, you have a wagon, I think is what it is, and you pull with 30 pounds of force at an angle of 60 degrees. And we want to know, and you pull it a distance of, it says 200 feet. And we want to know what's the work done.
Oh, we have an angle. So wait, what was on the angle?
So here's the thing. If we could write this as two vectors, then all we got to do is take the dot product.
Yeah.
Right? So on one hand, I'm going to put them both here at the origin. Here's the point of application, so that's the origin. We have one here at 60 degrees, and a magnitude of 30. The other one, how long do you want to make this vector?
200.
200, right? 200. Now, we could say, okay, well, this is the vector 200, comma 0, and this is the vector, and then we'd have to figure out what it is. Or we could say, and let me go ahead and give these names. Here's my force vector. Here's my direction vector, and I'm looking for f dot v, because I know that that's the work. But remember, there's a nifty way of writing that when you do have the angle between them. We happen to have the angle between them. F dot d is just the magnitude of f times the magnitude of d times the angle between it, which is 60 degrees. This makes our life much easier because look, all of those things are there. You don't have to find, you could if you wanted to find the components. That's something we'll be doing very soon. Okay, it's time to go. That's something you'll be doing very soon, is finding where the components of this thing. But in this case, it's just 30, which is that 200 times cosine 60, which I believe is 1/2, which works out to 3,000 foot-pounds, because it's in feet and pounds, foot-pounds of work. Oh, just so you know, I did work this out, and it does come out to be 15 times 30 root 3 over 2. And if you took the dot product of those two things, f dot d, you would have
3,000, comma 0.
Exactly. You'd have 15 times 200 plus 0 times the ugly thing that it took you forever to figure out. And you'd have a 0, and then it turns out to be, oh yeah, 3,000. So it does work both ways, just so you know.